Now that we've looked at hydroboration of alkenes, we can take that a step further and see what happens when we oxidize that alkyl borane. And this is certainly one of the many synthetic utilities of alkyl boranes is their oxidation, because in their oxidation, the product of that oxidation is alcohols. And the reason why that's important is because alcohols can be used for a variety of functional group transformations. This was so important of a reaction that an American chemist, H.C. Brown, won the Nobel Prize for his work in studying the oxidation of alkyl boranes. Now, why? Well, if we recall the reaction of an alkene with water in the presence of sulfuric acid, right? So we hydrate an alkene, and when we hydrate an alkene, we get an alcohol. Now we know that the OH of that addition of water, the OH always goes to the more substituted carbon because we're going to form a carbocation, and then water attacks that carbocation and then undergoes deprotonation. And we call this Markovnikov addition. So here we have a Markovnikov addition. The hydrogen goes to the carbon with the most number of hydrogens, and the OH, the nucleophile, attacks the carbocation. But now, notice, in this type of reaction, I can never make a primary alcohol because primary carbocations are never going to be formed, and they're never going to be the more stable carbocation. And therefore, there's a gap in the synthetic usefulness of this reaction, in that I can only make the more substituted alcohol. However, if I take this same alkene and I react it with BH3, I know the product of this reaction is that the hydrogen adds to the more substituted carbon. So it's almost a reversal of Markovnikov addition. And of course, BH2 adds to the carbon that has the most number of hydrogens, the least substituted carbon. And so if I can envision being able to remove that BH3 and replacing it with an OH group, in other words, oxidizing the alkyl borane with hydrogen peroxide in the presence of hydroxide, then I can get an alcohol in which the OH is on the least substituted carbon. And this type of reaction is known as an anti-Markovnikov addition because the typical addition, hydration of an alkene, has the OH going to the most substituted carbon, and now this hydration of an alkene forms the OH going on the least substituted carbon. So let's take a look at the mechanism of that oxidation. We already know how trialkyl boranes form, right? So assuming we have a trialkyl borane, we've reacted an alkene with borane and it's gone through multiple hydroborations. And so now I take this trialkyl borane and I react it with hydrogen peroxide in the presence of hydroxide, and I get 3 equivalents of alcohols, so 3 ROHs, and boric acid as a byproduct. The first step of this mechanism is the reaction of hydrogen peroxide with sodium hydroxide or potassium hydroxide, right? So the hydroxide's a base. It's going to remove a proton. I get the conjugate acid now of hydrogen peroxide. The conjugate base of hydrogen peroxide. So notice this conjugate base is a good nucleophile. Now, what do we know about boranes? Well, the boron has an empty p orbital. And so I can take that trialkyl borane and I can react it with a nucleophile, which I've just formed. And so that nucleophile donates electron density to the empty p orbital of boron, and I get this species where now the boron has a negative charge on it, right? And so what happens? Well, the next step is I get migration of one of the alkyl groups to the oxygen. So in that process, hydroxide is kicked off. That forms what we call a borate ester, right? So BOR in the process. And then, of course, notice hydroxide is kicked off. In the next step, what's going to happen? Well, this process is going to be repeated. So I'm going to take now my monoborate ester, and I'm going to repeat 2 times until eventually I get a trialkyl borate ester. And so now, and notice hydroxide is forming all the time, and I have hydroxide present, and so I can react that ester with hydroxide. Again, the boron has an empty p orbital, and so it's still a Lewis acid, so hydroxide can react with that, that ester, and I get this particular complex, right? And so now once this tetrahedral borate forms, I can lose one of the OR groups, and I get this, right? And so now I'm going to simply repeat this process 2 more times. And this is how I'm going to get boric acid. And now notice I get 3 alkoxides at forming, right? Well, this is in water. And so the hydroxides are simply going to be protonated in water, and it's going to yield the 3 equivalents of the alcohol. So I'm making the alcohols here, and obviously for every 1 equivalent of the trialkyl borane, I get 3 alcohols, 3 molecules of alcohol. And so that's how that mechanism works. And the key is that I can now take something like 1-butene, treat it with BH3, THF, followed by an oxidative workup. So notice it's important when writing reagents that there are 2 steps here. I have to put 1 BH3 THF, 2 hydrogen peroxide and OH minus. So why is that important? Because if I didn't have the 1 and 2, that means everything's in the same pot, and that certainly does not work, right? So I have to make the trialkyl borane first, and then I can oxidize that product. And the result is that I get the OH on the least substituted carbon. So here I'm now able to make a primary alcohol. Whereas if I took 1-butene and reacted it with water in the presence of sulfuric acid, I would get 2-butanol, right? So now I'm fine-tuning my synthetic skills and recognizing how I can place an alcohol across a double bond. And that's kind of the fun thing about synthetic chemistry. You use the tools that you know to devise synthetic strategies to, place functional groups where you want to place them. So, if I take here 1-methyl cyclohexene, treat it with notice B2H6 diglyme. So B2H6 is, if I don't, remember I said if I don't use THF or diethyl ether, BH3 tends to dimerize. It dimerizes into B2H6. Well, you can actually buy B2H6 in diglyme, which is a high boiling point solvent. But it works the same way, right? B2H6 is weakly coordinated, and so you get free BH3, free borane present. So I'm just showing you a different look of hydroboration. And then, of course, reacting this with hydrogen peroxide in the presence of sodium hydroxide and water. And what do I get? Well, I get this. Right? So I get trans 2-methyl cyclohexanol. Always trans 2-methyl cyclohexanol. Now remember I said this is a syn addition. So why am I getting trans 2-methyl cyclohexanol? You always have to keep in mind what the syn addition is. Remember this is via the hydride and BH2 adding on the same side as one another. And so now when the BH2 gets oxidized into OH, the OH and the methyl group are trans to one another. The OH and the hydrogen are certainly cis to one another, but the hydrogen and the methyl group are trans to one another. And so now you start to see kind of not only the regio selectivity of the reaction, but the stereo selectivity of the reaction as well. And so this is a nice little introduction to addition reactions of alkenes. And in the next chapter, we're going to see that if we understand the behavior of the electrophile or the Lewis acid, we can really understand a lot of both regiochemistry and stereochemistry of addition reactions.